Okay, good morning everyone. So, we will start with the introduction to the subject. Mainly we are looking for application in mineral processing and coal processing. So, the entire day we will devote on introducing the what is mineral processing, what is coal processing. The mineral engineers may be thinking that it is they already know, but there is nothing wrong in knowing it again. And during the introduction, I will also try to introduce that what is fine and ultrafine particle, why we have to understand fluids also, and the fluid mechanics and solid fluid interactions. So, that is basically the objective of today's 3 lectures. Okay. Now, if you look at the subject introduction to mineral processing, you may be having one student asked me as a chemical engineer how I can contribute or what is the usefulness of this course for me. You look at this is basically an interdisciplinary branch in engineering, relatively newer branch in engineering, where the major professionals who are in this field, they are the conventional mineral engineering graduates. We have geologists, applied geology people, metallurgy people, chemistry, chemical engineering, mechanical engineering, electrical engineering, mining, I may add software engineers, computer science, instrumentation, anybody can contribute in this field. Okay. Now, there is some confusion about the name also. Sometimes it is called mineral engineering, ore processing, mineral beneficiation. These are all to some extent deal with the similar type of aspect, but when you give more emphasis on engineering aspect, we call it mineral engineering, more of a process related thing. So, there is some finer deviations into that, but in totality we discuss about that. In case of coal, we call it coal washing, coal processing, in generic nature we call it coal preparation also. So, before we start with that, we must understand what is that mineral, what is an ore and all this. Now, if we look at the definition, that is the textbook definition of a mineral, it is basically the natural inorganic substances. So, it has to be naturally occurring inorganic substances possessing definite chemical compositions and atomic structures. That is the textbook definition of minerals. Now, what is the ore then? So, an ore can be described as an accumulation of mineral in sufficient quantity as to be capable of economic extraction. What does it mean? That means a mineral where I have got a certain element present which I can extract it and sell it to have a profit, that is a business. Then we call it basically an ore. Now, how much that should be? It varies from mineral to mineral. So, the metal content, that is called the grade, required for a deposit to qualify as an ore varies from metal to metal. I give you an example like gold. You know, gold what we are recovering, what we are mining and processing and converting into as a metal, you know how much is gold available in that ore? It is in ppm level, that is the highest grade gold what we get in Australia or some part of South Africa, they are having around 2.5 ppm. That means, in 1 ton of ore you have mined, you are having on an average 2.5 grams of gold. 1 ton of material, I repeat, you are having 2.5 grams of gold, and that we call it very good grade of your deposit, gold deposit. Whereas, in case of iron ore, if it contains less than 15% metal, we call it that this is not a ore. Why? That is the relative abundance. the technologies you have to extract, to process and all this. So, ultimately what matters? This is the basically, because when we talk about engineering, there is a business associated with that. I must make profit out of that. So, and basically if the contained value per ton, what is the meaning of contained value? That how much of metal is there in per ton of material what you are mining. If that is greater than the total processing cost, here process does not mean always mineral processing, it includes everything starting from your exploration, mining, mineral processing, extraction, everything, okay, plus your losses, because what will happen when I try to extract 2.5 gram of gold from 1 ton of material, I cannot extract the 100% of that, I will be losing some of the material. So, how much I am losing? So, what are the losses? And other cost like your what you are going to do with the waste materials. 2.5 grams you have extracted, what you are going to do with the remaining material, that will cost you. So, if you can convert that into a value addition, then my contained value per ton goes up, or otherwise it will add up to the right side of this. So, if in totality if that is greater than that, then we call it as an ore. So, today what we are calling it as a of low grade, or it is not an ore. Tomorrow maybe there is a technology to extract it in an economical manner and we make profit out of that, that can be qualified as an ore. So, that is the basically. So, are you clear about this? I hope so. Okay. Now, some important minerals, you know, this you can be familiar with, that is your bauxite, these are all minerals name, these are the chemical formulas, there is no point in wasting time in talking about that. So, you must be familiar with the name of the minerals. We are not mining metals, we are mining ores. Okay. Now, what is mineral processing then? So, it is a process in between mining and metallurgy. That is why mineral processing is required to upgrade the mined product, as I said before. That is, I give an example like say copper. What you are getting the copper as a metal, you know what is the percentage of copper present in your ore? What is the ore of copper? That is chalcopyrite, normally we use CuFeS2. So, normally we have around 1% to 1.2% of copper in that, and I cannot directly put it into a furnace to extract it. So, the metallurgical requirement is I must have a minimum copper content of 36.5%. Now, how do I enrich it from 1% to 36.5%? By some cheaper means. So, that is the subject of mineral processing where we deal with that. That is, we exploit the property differences between your wanted and unwanted minerals, like your difference in density, difference in size, that is basically the hardness, then difference in your electrical properties, magnetic properties, so many other properties are there, we will discuss. Okay. So, that is basically the subject of mineral processing. Now, the sequence of operation is like this, like your mine product, you have got an ore, then what do you have to do? I will explain it again at a greater depth, that is, you have to first break the material into smaller sizes. So, the particles which I want and which I do not want, they should be dislodged from each other, then only I can separate them based on density differences or size differences or some other property differences. So, that is the separation process. Then you have to handle the product again, that is, how do I send it to the customer, that is large tonnages of material, because here we are handling large volume of material, the tune of 10,000 tons per hour, 5,000 tons per hour. So, the material handling system should be robust to handle this amount of material per hour basis. You look at some of the mining operations, I am just showing you some of the pictures. That is, these are basically different mining methods. What I want to highlight here, that is the scale of operation, and in the process you see that there are so many your mining machineries they are being used, and you cannot control the size there. So, what will happen? You will be having very coarser particles, finer particles, medium sized particles. So, you will have a distribution of different particles which you cannot control, because we have to mine large tonnages of material per unit time. Okay. So, that is where you generate fine and ultra fine particles. Even the environmental monitoring and all this are basically the such it becomes a problematic area due to these operations. Okay. So, the first step after you have mined, in mining also, how do I do mining? The basic in short, actually you have to first break the material. So, we call it blasting. We use explosives and then we break them into a sizes which are basically we can handle it with my bulk material handling equipment. And then it comes to the processing plant. Why? Though at that sizes the particles may not be dislodged from each other, that is our wanted and unwanted. I will explain it. Okay. This is what I am trying to explain. Suppose I have got a particle like this. I have got the miners they have given me, and my wanted material are these particles. Okay. Now, first thing what we can do, that is I have to dislodge them from each other, otherwise how do I separate? Now, suppose that these particles are having a specific gravity of 7, other associated materials they are having a specific gravity of 2, then if we break them into a finer sizes, then what will happen? I may have different type of particles, like say suppose I change the color from this to black, where I will have a pure blackish material, that is my wanted one. I can have pure whitish material, that is my unwanted one, but unfortunately we will have some material which are combinations of again this wanted and unwanted. So, that is called, we call it liberation. Okay. So, if I want all the particles to be free from each other, that is black and white segregation, then what it needs? That these particles again have to be broken to a very finer sizes. By doing that, you consume more energy to break them. So, energy means it cost, and then as the sizes become finer and finer, which in this course we will discuss, your processing cost also goes up, your environmental problems become more and more difficult to deal with. Okay. So, there is an optimized condition I have to look at. What is the condition for optimization? That is your profit. That is, if I separate them at this sizes, now say suppose if I discard this and these particles which are free from the black particles, relative grade will go up, relative percentages of my black particles in that assemblage will go up. Now, will the metallurgist buy that? Can it give me 36.5% copper contained into that? If it meets that requirement, we restrict to our size segregation to that size. If it does not, what we will do? We cannot break it further again, because that is a wastage of energy. What do we do? We try to segregate, we try to take it out from this assemblage, the particles which are already basically free from the dirt. Okay. And then we will put them again into further breakage. So, that is basically a cycle. That is why we talk about flow sheet, that we need number of unit operations, and there is like your computer program or algorithm, you know, you have got a do loop, you have to check that whether it conforms to the quality or not. If it is not, you recycle it back, going for the iterative loop. That is how we do it, that is what we will discuss in this course. Okay. So, in the size reduction process, when we are breaking it, the naturally the minerals are crystals and they have a tendency to break into endless numbers of sizes and shapes. What I am trying to say, that is, if you put a particle and if you give some kind of your stresses into that it could be some kind of mechanical stresses or something created by some means, they will have a tendency to follow a distribution like this, that is from a wider distribution from very coarse size to very fine sizes. This x axis is basically the sizes, and this is how much of that is basically passing sizes. Okay. What is the relative percentage into each size intervals. Okay. So, we do not have any control in that. That is what we are having in the blasting operations, because there I have to blast a rock which is having in situ stresses and all this in a deposit. So, there we are having a fragmentation, that is for your mining excavation purposes. But our job as a mineral processors, we want to reduce the generation of these finer sizes, because we want to take out my material at the coarsest sizes possible, so that my energy input is less, so that my profitability goes up. So, the challenge here for a mineral processor, that how do I make this curve as vertical as possible. So, that is the challenge of a mineral processor. So, the trick here is, that is when producing quality products from rock or minerals, is to keep the size reduction curve as steep as possible. The shorter or narrower fraction, the more the value. Okay. It is easier to say, but it is very difficult to control. To achieve that goal, we need to select the correct equipment and the sizes, the scale of operations. How do I do it? So, for that, that is basically dealt with by the solid mechanics people. It is another domain of your this subject that we are not going to deal much in this course. Okay. But that is the size reduction, that could be another course, but we are not going to deal with that here. So, they are all different when it comes to reduction technique, because how do I do it? Then what is essential? I have to know what is the characteristic of my rock. That is my rock which is hosting my minerals, and that is a heterogeneous. What is the heterogeneity coming from? That is, it could be having a different density distribution, different hardnesses, different textures, different morphologies, different properties. Some of these properties we will talk about tomorrow's lecture. Okay. What are the properties we have to look at? Then what do we do it? So, what are the combination processes? Just to give you a very brief introduction to this. So, when we deal with basically so here the objective is to liberate the valuable minerals from the gangue in a controlled manner. So, depending upon the particle size we deal with, we name them. We call it crushers, we call it grinding. When we deal with very fine material, we call it further breakage is required, we call it grinding. For coarser material, we call it crushers. Okay. So, if we look at in the crusher also, there are different types of crushers are there. We call it primary crushers, secondary crushers, tertiary crushers, so on. Okay. Now, you look at some of these crushers. My emphasis is that you see that even in this breakage stage, we cannot control the generation of fines and ultrafines. We try to control it, but we cannot control it 100%. So, this crusher, what happens, you have got a solid, your very hard surfaces, and then this is a rotor type of system and it rotates. So, when it rotates and the particles are coming, you want to reduce their sizes and you are putting compressive stresses. So, because of that, it is getting broken, and unless and until all the particles are finer than this gap, they will be still under the stress and then they will be broken. So, what it is telling that you very difficult to control the sizes. Okay, the topmost size you are controlling, but the finest sizes it is very difficult to control, and that is the trick, that how do I do it. Okay, that I will tell. Then look at the scale of operations, the jaw crushers, some of the crushers, you know, look at the sizes, the dimensions. Now, if when you look at the dimensions and all this, I do not think that mechanical engineers have got any doubt in their mind that there is a huge industry for me where we can contribute, because the bigger machine means more of mechanical engineering. And when we are dealing with rocks, normally naturally the wear will be a very big problem. So, you need to select the appropriate materials. So, you see the opportunities for metallurgist to come out with a new materials, that is where my wear will be less, how do I control the wear and all this. Because the problem here is that if something is worn out inside, it is not only the material cost what is important, it is the downtime cost, how much time it will require to replace it. And these capacities are like 10,000 tons per hour, and say suppose the replacement time required is 8 hours. So, 80,000 tons of material, where you will stock it. So, you have to stop the mining operation also, and downstream processes, metallurgical extraction processes also have to be stopped. Because of what? Because of one part key component has owed out. So, there the challenge for the material scientist is coming, that is how do I develop a better material so that my wear is less. So, I have answered the question to mechanical engineers, metallurgists, I will keep answering, okay, that why I have allowed you people to join this course. Okay. Then you look at this cone crusher, that is another crusher, it is a similar type of your operation, how it is breaking. So, you see that there is a size distribution, that there are many sizes coming out of that system. There is another type of crusher, these are called rows, which are basically being rotated into an opposite directions, and then you are squeezing the materials to pass through that, and you are basically crushing them, breaking them. So, this is basically my do look, that is what we use it in between, that is we have screens. So, what do we do? After a crusher, if I put a screen, what will happen? Now, say suppose I want all my particles, suppose my starting size is 100 millimeter, I want entire material to be broken down to below 10 millimeter, and for that I have selected a crusher. Okay. Now, what I will do? I will put a screen of 10 millimeter aperture, and then I will take out the particles from the system which is already finer than 10 millimeter. Are you getting my point? Then whatever is in between, that is within 110 millimeter, I will be having on top of that screen. They will not be able to pass through the screen. You understand what is the meaning of screen? Suppose this could be a screen surface. Okay. So, any particle which is finer than this aperture, they will pass, coarser than that, that will retain. So, these particles I will again resend it to my crusher to break it. That is how I am trying to control, but still you cannot avoid the generation of your finer. So, what is the definition of fine here? I want below 10 millimeter. The below 10 millimeter is a generic term. So, below 10 micron is also below 10 millimeter. Say below 9 millimeter is also below 10 millimeter. So, I want my particles to be just close enough to 10 millimeter, but that we are not controlling. It is very difficult to control them. So, in the process we generate fines and ultrafines. So, the definition of fines and ultrafine changes from my application, from my technology availability. What are the problems? That is how I look at the definition of fine and ultrafine. Okay. So, these are some of the screening operations which we are not going to discuss in detail. I just wanted to show that these are the unit operations available with us. So, this is how the entire my iteration loop, and is like your flowchart you write, if then you give the conditions like that. Here what it is saying, that I have got my mind over here, I have got a crusher, and here the particles I want below 150 millimeter, I have got 150 millimeter, then I want to take them or say to take out 12 and 19 millimeter, basically the particles. I have got two screens here. So, whatever is basically coarser than that, I can send it to another crusher, like that I can keep on interrogating, still I get my desired particle size. That is how we control it. We try to control it, but in the process, I repeat it again and again, it is impossible to control the generation of relatively finer and ultrafine sizes. So, in grinding, now many times for this liberation, like for gold or for copper, say for example, so for copper ore, normally the characteristic is that the particles, they will be liberated to a basically a limit which is basically acceptable by the processing people, and you can process it in an economical manner. That size becomes around 40 micron, 40 micrometers. Now, you are having a lump of say 1 meter, 2 meter, and that you have to break it to below 40 micron. How do I do it? So, you do it by stages. You have crushed it, and what happens when it is becoming finer and finer? The surface area generation is more and more. And which one will consume more energy? Suppose from 100 millimeter to 10 millimeter, 10 millimeter to 1 millimeter, which one consumes more energy? 10 to 1. Why? Okay. So, that is why when you are going for a finer and finer sizes, your energy consumption puts up. Okay. So, there we use basically a combination of different forces into a machine, because we need more energy, more input energy. So, here basically we try to use first impact or compression, along with that we want to use chipping, and also we want to use abrasive forces. Okay. What are the machines looks like? It is like your grinding mill. So, what do we have? You have got a tubular type of structure where you put your material. Along with that, we also pour some steel balls which are much harder than my material to be broken, and then we rotate that tubular machine, that is called basically the tumbling mills. And because of rotations, what will happen? So, when it is being lifted towards this, there will be abrasion, that is abrasion between the surface of the machine and the particles. There could be abrasion between particle and particle, that could be abrasion between your balls, that is steel balls, and the materials. So, there could be many types of abrasion is there. So, abrasion generates much more finer material, and then when it is lifted, and then if we allow them to fall freely. So, that is a calculation, that is what should be the RPM of this. So, suppose say if my RPM is very high, then entire material will be rotated, there is no breakage. So, that is called the critical speed. There is some calculation, but we are not going to deal with that in this lecture. So, we allow them to fall freely. So, which one will be carried further? That is the particles which are having more mass. Normally, the steel balls will be coming down at the later stage. Before that, your particles will come down. So, when the steel balls come down here, they will hit the particle again. That is how you are introducing impact in that. That is, you keep on doing that, and after that there is basically a gradient is there is the type of machines you have, bigger machines, and then they are normally we also introduce water into that. Why? Now, because that water helps in many ways. One is basically transport of material, how the material will be transported, suppose from this end to this end, how the materials will be transported. It helps also in segregating my particles, that is otherwise when you are basically breaking the particles, there may be a chance of again further agglomeration of that because of incipient fusion between the particle surfaces. So, that water helps in dislodging that surfaces, okay, so that they are basically into a fragmented stage, into an individual stage. That water also helps because when you are rotating it, there will be a lot of heat produced. So, then because of the heat, what will happen? Apart from energy losses, there will be more wear, because at a high temperature the wear is basically more, wear of these surfaces, wear of my balls, wear of my machine components. So, that also helps. Then it reduces the noise also, because it will be very noisy. So, your environment wise that is not also correct. So, that is why the water plays a huge role. And how the, so basically here also your solid fluid interaction starts. This is what Mr. Kaushik Sengupta will talk about, that in the industry how do they handle these issues, and these mills are very big sizes. These days it could be your 3 meter diameter or maybe 4 meter diameter, and 8 meter long mills are also available. So, 8 by 4 meter or 5 meter you think of, okay. It is huge machines. The capacity could be 12,000 tons per hour, okay. So, that is the scale of operation we are talking about, okay. Look at this is the gentleman standing, and you look at the size of this, height of this mill. So, this is type of, so there are now various developments are there. We call it semi-autogenous grinding, where we try to reduce the load of my steel balls. The autogenous grinding, the concept is that if I have got a wide differences in my hardnesses of my particles to be broken, then we can break my relatively softer particles by impacting by the relatively harder particles, but that is where I will use them, that is basically dictated by your material characteristics, okay. So, this type of machines are there. Now, so we have prepared my rock to a separation for a separation process. We have broken them into pieces. Now, the separation comes. How do I separate them? My wanted and unwanted materials. The separation methods may be grouped into 3 different categories, broad categories. One is physical, that means where we are exploiting only the physical property differences between our wanted and unwanted materials. Then physico-chemical properties difference, like the surface, the properties, that is your chemistry of the surfaces and all this. So, that is called the physico-chemical properties, and sometimes it could be the chemistry, by using some chemicals we can take out of them. We will briefly discuss about that. So, the chemical processing, what is chemical processing? That is basically to separate desired metal or compound from the finely ground ore by dissolution. That is, I have separated them. Suppose a mineral we found that to separate it based on the difference in density, you have to grind them to a size below 4 micron. So, the energy cost, energy requirement will be huge, that may not be economically viable. So, what we are trying to do in that case, that is break it to a size where, and then after that you pour some leachant like your acid, okay. Like I can put hydrochloric acid, I can pour sulfuric acid, nitric acid, depending upon the characteristic of my mineral, okay. And then I can convert them into a stage which is basically can be brought into my solution. So, selectively I am bringing it my metal into a solution, then you go by the electrowinning process, electrolysis process, and so many other processes to get the metals. So, your metal extraction route is different, okay. So, that is what we call it leaching. Many times, suppose your gold, platinum metals, gold, you know, the basically the extraction route, I do not know how many of you are familiar with, we use cyanide. That is a very good use. If there is no cyanide, there is no gold. People are researching on the alternative methods to replace cyanide, but still it is not commercially available as far as I am concerned. So, cyanide, what we are doing? You are converting into gold cyanide, then you are basically taking it out. Then we are also using sometimes the bacterias, that is called the bio-leaching processes. Like in many ores we have got pyrites, like even for copper CuFeS2. So, there are some sulfur reducing bacteria are there, thiobacillus thioxidant, thiobacillus ferrooxidant, like that type of bacteria are there. With these bacteria, that is the natural tendency that they oxidize the sulfur. So, the sulfur gets converted into sulfur oxides, and then you can convert them into sulfuric acid, you can generate, you can use it for fertilizer thing. And when the you have withdrawn the sulfur from CuFeS2 matrix, then the bonding between Cu and Fe is basically loosened, and then you can separate the iron from that copper, and then that is where the use of bacteria are coming, okay. But the challenge there, engineering challenge is, that is, how do I introduce the bacteria? How do I create the environment where the bacteria's growth will be exponential growth, otherwise not have. So, even in these two processes, you can understand that I have to deal with some liquids, whether it is acid, whether it is some form of water and mixture of bacteria. Again the solid fluid interaction is coming, again the fluid mechanics plays a dominant role, and you are dealing with fine particles. So, what is the fine and ultra fine? I keep repeating, these are all relative terms. There is no perfect definition. It depends on what material you want to process and what are the technology available. Okay. Now, I will show you some of these, like your hydrometallurgy of gold, that is basically you are taking the gold and you are basically leaching with cyanide and you are converting into a gold cyanide, and these are the processes, and you see that invariably you are not giving 100% pure cyanide. So, you are diluting it. So, that means now what is the kinetics of there, that is what size I should get. There I can go to the board, tell you that that is called basically a diffusion process. Like if I have a particle structure like this, if I have a particle this, then my solution, say suppose HCl. So, when I am putting a acid, so what is the surface it can react with? That is the available surface is this one, isn't it? Now, whatever metal is there, if that is coming into solution, then only it can reach the next layer. When it comes to the solution, then it reaches the third layer, like that. So, what will happen? If my particle size is very big, the kinetics of this process will be very slow. So, there is a compromise sizes, that is depending upon the kinetics of the processes and how fast you can do it, because my capacity is very important, that is per unit time how much of that material I can process. So, here the size will depend on what is the characteristic of my material. Okay. Now, in hydrometallurgy there are basically aluminum process, bare processes, the metallurgist people, metallurgy students, I do not know whether you have already taken a course on extractive metallurgy, you will be going through these processes. What I want to emphasize that even with the hydrometallurgy processes you have to deal with solid fluid interactions. Okay. Now, what is bio-leaching? I said that this is microorganisms we are using, but here invariably you have to deal with water and air. You have to supply oxygen for the bacterial survival. So, you are having a basically different fluid system, different phases you have to deal with, if you are dealing with the engineering aspect of that. So, I call it the world's smallest miners are basically the bacteria. They are already in commercial exploitation, it is there, but where it will be applicable or not, that depends on the nature of my ore and the nature of my deposit. Okay. Now, that is about the chemical part. Now, physico-chemical processing, here the objective is that is I want to separate my finely ground materials by modifying their surfaces. What do I mean by modifying their surfaces? Like if I have two particles, if I put it into water medium, and after some time if you take out these two particles, I will look at under microscope, you will find that there is some water layer on surfaces on some of the particles and there is no water layer, or the water layer is very thin in another particle. What it is telling? That the surface properties of my particles are such that some particles they like water, we call it hydrophilic particles. Some particle surfaces they do not like water, we call it hydrophobic particle. So, that is basically the surface chemistry phenomena, we try to use it, and that is what Dr. Subramaniam is also working on, that is the area probably in his lab, there are a lot of people they are working, and is not only the only water medium, sometimes we inject some chemicals to modify the surfaces, we will talk about that. So, these processes are called froth flotation, probably at 12th level some of you have studied this, what is the froth flotation. Okay. Then there is another one is called selective flocculation. So, in a froth flotation what we do? I will show you this picture, because I have got a cell suppose, and now I pour my material into a form of slurry, that is a mixture of water and my particles, and there I stir the entire thing, so that my particles are in suspension, otherwise they will settle. Okay. There are some designs where you can inject air also through the stirrers inside if it is hollow, and if you have got some your pores here, then I can inject air at some pressure. So, when I am injecting air where through basically a water bath, then what will happen? The bubbles will form. So, these bubbles will try to rise up. Okay. Now, think of the scenario. Normally, it has been observed the particles which are basically hydrophobic, they are aerophilic. If they do not like water, they like most of the cases air. So, they will be attached to the surfaces of my air bubbles, selectively the hydrophobic particles, they will be lifted up, and there will be some foaming type of, we call it froth. The froth will be formed, and before the froth breaks, that is the again I have to know when it will break, that is the froth chemistry, stability and all this. If I can take them out by some mechanical means, I can separate the hydrophobic and hydrophilic particles. A good example of naturally hydrophobic material is coal. Coal surfaces are naturally hydrophobic. Okay. But the degree of hydrophobicity depends on contact angle. So, there are methods to do that, but that is outside the scope of this talk. Okay. So, many times the degree of hydrophobicity what we have, that may not be sufficient enough to achieve my desired separation. So, what do? We add some chemicals which we have designed in proper way that it will adhere to the surfaces of my materials, which will make them more hydrophobic. Okay. So, then what will happen? The degree of hydrophobicity goes up, and then you can recover them more selectively. That is what we call it collectors. The froth, as I said, that it needs some stability. I have to have some time to take them out, even for mechanical operations. So, sometimes the froth may not be stable because it has to withstand the atmospheric pressure also. So, there we add some chemicals again to make the froth stable, that is called the frothers. Sometimes we have seen that this activity, the entire, because it is a physico-chemical properties, it is a surface based chemistry based phenomena. Many times the pH of the system also is very important. In acidic pH, sometimes it works better. So, if I want to make it acidic, I have to use some acid into that. So, sometimes it works better in alkaline environment. So, that is called the pH modifiers. Sometimes what happens, suppose I want to separate two particles, but both are hydrophobic or both are hydrophilic. How do I do it? Then what do? We try to use some chemicals which will sit on surfaces of the selectively on some of the particles, which will try to force it to stay there. That is called depressions. That is, intentionally you are modifying the surface of the particle so that the degree of hydrophobicity loses. So, it is not going up, that is called the depressions. So, like that, there is a huge industry, many people are working in this area, and there is a huge demand for engineers, where like your chemical engineers, people from chemistry, people from even computer science, they can work together on synthesis, on designing and all this. If you have an opportunity, you visit one day the TRDDC, actually Dr. Subramaniam's your laboratory, you find that there are experts who are basically designing this reagents and all this. I am sure in his talk he will talk more about this. I leave that aspect to him. Okay. Then there are basically, so here what I have to know, you see again that I have to process large tonnages of materials. So, this is an unique example where the engineers or the basically the people from different background, they can work together. There is a lot of fluid mechanical behavior is involved, that is your bubble particle interaction, solid fluid interactions. So, it is a multi-phase system. Then your chemicals, how do I add them? How do I ensure that my chemicals what I have added, they have adhered to the surfaces of my desired particles. So, suppose I am adding chemicals here, how do I make sure that there is a mixing of these chemicals even properly? So, it is a mixing phenomena, it is basically your say actually similarity it is having with the reactor designs and all this. So, the chemical engineers they can work here, mechanical engineers they can design the your cells having, because both of them they are having exposure in design as well as in fluid mechanics. The physicist they can help us in knowing the basically the froth stability, that is what will be the size distribution of my bubbles, how do I control them. If I blow up, basically when we are kids, you know, you used to blow up the soapy waters to generate froths or bubbles, and probably you have noticed that some bubbles they break immediately, some bubbles they stay there for a longer duration. What causes it? So, that is the mechanics of that we have to understand. There again the mechanical engineers can be of use, the CFD can be of useful, the fluid mechanics is a complex fluid mechanics can come into the picture. Then when I am using the pH modifiers, so many chemicals and all this, so the materials also plays an important role, that what will be my material for that, so that I do not have wear and all this. So, metallurgists they can work here also. So, and of course, the chemistry people, because here the one aspect is that your proper reagent selection, reagent designing, that is tailor-made designs depending upon the properties of my particle surfaces, what should be my ideal chemical, that is a synthesis and all this. So, it is a true multidisciplinary area where we can work together. Okay. You look at this is one modification to this, the design modifications, that is called the column flotation cell. Principle is identical, almost similar. Only thing they have changed that you see that L by D ratio they have changed. Why? Now, you are giving more residence time of the particles to be carried, and you are having a distinct difference between your froth layer and your basically the slurry level. So, here the particle the distance is less. So, maybe my unwanted materials they may be also are being carried because of entrapment or entrainment phenomena. So, you are allowing them to drain out, and I want to get a cleaner product. But when you are giving more residence time, definitely your capacity will be less. So, that is the challenge, that is how do I. So, the scale up is a very big factor, again the entire designing aspect is coming, how do I scale them up, what is the fluid mechanics, what will be the scale up factors, how do I simulate them, all these challenges are there apart from the chemistry and material part. Okay. So, these are basically the industrial flotation cells. We can have a different batches of cells, a cell could be as long as this room, and there could be a different compartments, that is you deal with, suppose even many times the problem is the separation, like I give this example lead zinc ore. You have got PBS, galena, ZNS sphalerite, and sometimes you have got copper mineral also in that, you have got cadmium, sometimes you have got silver, they are all wanted. And the main problem comes, even the mineral processing deals with the separation between wanted materials. I want PBS, I want ZNS, I want CuFeS2, but all of them if I put into a furnace, can I extract lead, zinc and copper? So, how do I segregate them? So, even mineral processing does not always mean that I have to separate wanted and unwanted. Even with the wanted, amongst the wanted material, I have to separate them. So, that is also a challenge, that is also the part of the mineral processes. Okay. Now, that is why what we do, if I have a complexity of the materials like that, we try to separate, say suppose rougher cells, suppose we have decided that we have to go for a flotation cell. So, in a rougher normally we target, there is no say clear cut rule, it depends on the ore characteristic. I may try to first separate out my unwanted material like silicates, like lead zinc ores. I have got unwanted material as silicate, I do not see any value in that. So, I will try to discard first my unwanted materials. Then I have got some your wanted materials, but I want to separate them. So, we call it cleaner 1, cleaner 2, cleaner 3 like that. So, the different cells I am having different type of atmosphere, I am having different types of reagents to be added, and what reagent, what conditions, what RPM, what will be the hydrodynamics of that is basically the design aspect of that. So, what is the core competence you need? One aspect of this, that is you can see that what should be the design of a machine, what should be the mechanism of bubble generation, how do I generate bubbles, how do I control their sizes, and in an atmosphere where I am already having slurry, how do I control that. So, that is where the core competence required is basic knowledge of fluid mechanics related to fine and ultra fine particulates and all this. That is why this course is. So, we will try to explain all this, the basic fundamental principles, and some of the applications we will try to show you that how the basic knowledge of fluid mechanics can help you in better understanding some of the processes. Okay. Now, this selective flocculation, many times what we do, that is your aggregation of fine particles by surface charge reduction like your pH, ionic strength and all this hydrophobic interactions, you can add some polymers, that is also called flocculants. Okay. Like I give you one example, that is you have used water. Now, at the end of the process, I have to recycle back that water, otherwise my water cost will go up and my water pollution will go up. I am not allowed. So, how do I separate water from my solid? Okay. So, that is a solid liquid separation. So, one of the processes is that is called a thickener, that is probably the picture is somewhere here. Okay, I will come to that. So, there basically what we try to do, you try to bring the particles, change the particles behavior from a suspension to a segregation of solid and water. So, how do I do that? I increase the particle sizes so that they settle faster. So, what I need to know, that is how do I know what is the settling velocity of the particles, okay, and what size I need to do, and there I add some chemicals to enlarge their sizes, that is called the flocculation processes. Okay. It is where now what polymer, what reagent I will use, that will be decided by the particle surface characteristics. Okay. Then separation of flocks from suspension, we have got a flock, but how do I separate it? It may be by, that is you have made a size enlargement, but now there are processes, I can pass it through a screen, I can also separate them, I can use a sedimentation process, like let them allow to get settled because of its mass, or maybe I can use a flotation process because the size enlargement is there, I can use a flotation again to separate them out. Okay. So, flock separation scheme determined by flock properties, that is your size, density, shear strength, that is what is the characteristic of that flock I have got, that will determine that what method we will go for that, we will use. So, various techniques we name it that distinguish the different techniques. One is called aggregation, that is group of particles held together in any manner, that is how the basically the size enlargement processes. Okay. Then we have got coagulation, specific type of aggregation process leading to formation of compact aggregates. Then flocculation, that is you are changing the structures, and then you have got a size enlargement processes. Here you see the people who are dealing with this type of your solid liquid separations, there the definition for sizes are different. So, the definition of fine and ultra fine changes depending upon the application. So, here they call it colloidal particles which are less than 1 micron, ultra fines are 1 to 10 micron, fines are 10 to 100 micron, and they call it coarse particle greater than 100 micron. So, and as I said, for iron ore, for a process engineer, below 10 millimeter is fine. For coal, below 0.5 millimeter is fine, and when I am going for a solid liquid separation, the coarse material is greater than 100 micron. So, when you look at an article fine and ultra fine, you must try to understand what is that size range they are talking about and why they are targeting that sizes. What is the problem with that size? Otherwise, you should not have bias in your mind that ultra fine means it's a nano size. No. Okay. So, that is the point I want to say clear from your mind, you know. Then selective flocculation, the separation strategy is that I add basically I have my particles, I have to ensure that they are dispersed, then you add a polymer, you try to form some aggregates like this, and then you bring them by basically the your separation of flocks either by sedimentation, you allow them to settle, or by some flotation, and then you are basically selectively removing these particles. Good example of this application is that is your iron ore processing. Iron ore processing, there the problem is the removal of alumina and silica, alumina silica ratio, maintaining of that. And in Dr. Subramaniam lab, one stalwart is there, Dr. Pradeep, he worked extensively on this selective flocculation. He actually has developed many reagents for this selective flocculation for iron ore slimes treatment and all this. Okay. And that he is still continuing, I guess, that type of research is being done. There are chemical industries like Cytec Chemicals, Nalco Chemicals, who are basically working rigorously on the designing of the certain polymers, whether you need high density polymers, low density polymers, short chain, long chain, and all this. So, there is a lot of research going on for these particles specifically. Even for iron ore slimes, you cannot have a generic type of polymers or generic type of chemicals. It is dictated by the formation, that is the geological formation of my material, because the surface property you do not have any control. You have to understand that by characterizing the surfaces of the particles. Now, what are the limitations of chemical and physico-chemical processing? The limitations are definitely create environmental hazards because we are introducing chemicals. So, what you are introducing, that will be coming back to you, because if I do a mass balance of that, how much of that being used, and after that you have to recover it. So, there will be some recovery efficiency issue. So, you have to discard some of the chemicals. So, where they will be going? They are going to the environment with your water or with your fluid, and they are basically creating environmental hazards, and the cost of the process goes up because of the cost of the chemicals. Okay. Then make the process cost intensive because of these chemicals and all this. Okay. So, these are the limitations of this chemical and physico-chemical processing. So, when the typical physical processing you say that it is not possible, then only you look for the opportunities by the physico-chemical or chemical routes, okay, because it is much more costlier than the physical separation processes. Now, what are the physical processing? As the objective is, that is to separate desired particles based on their physical properties, very common properties like density difference, shape difference, difference in shape like a flaky particle to a spherical particle. Okay. Then size, all this. Size is not directly the property of a particle, it is basically the hardness or the morphology of a particle. Okay. Because when you are trying to reduce the size, you are having a different sizes based on the relative hardness of my materials. Then it is accomplished by various treatments, like we can have different types of separation. There are many more, but I am just telling you these are the broader categories. We can have classification. Classification again a size separation process. Like I want to separate 10 micron and 20 micron particle at a rate of 5000 tons per hour. Can I use a screen? You imagine what will be the surface area requirement. You imagine the land requirement, imagine the cost of my screens. So, there we use again the principles of fluid mechanics to separate them. We will discuss that issue in detail in subsequent lectures. Then magnetic property differences, suppose some particles are paramagnetic, some particles are diamagnetic, some particles are having say different magnetic susceptibility thing. So, we can put them into a magnetic force, magnetic environment, magnetic force environment. So, some particles will be adhered to the magnet, some particles will not be, and then we can have a design, I will show you, and then we can have a separation. Then gravity separation, where we use the density difference of the particles to separate them. That is all for this first lecture. We will continue after 5 minutes again. Okay? So, we will go to the next lecture in continuation of this first lecture. Okay? Thank you very much.